upside down. This is just so bizarre. There. Let's try that. So now he's recording. And what we'll do is we'll just stick to the camera for now because it's just too iPad challenged. I'm going to go back to Zoom. But unfortunately I cannot. This is just bizarre. Well, it's can people see the Robert Johnson patent or not? Yes. All right. So for some reason, Zoom won't let me switch to full screen mode so I can see myself in Zoom. I don't know why. It's just bizarre, but there it is. I can't explain it. Maybe if I restart Zoom, but I dare not because I'm afraid. So anyways, let's see what I can do to increase the size somewhat. There. So what we wanted to do was take a look at this so-called twisted ring counter. And so what I would do is continue my analysis in with the document camera. And we'll ignore the iPad for now. And so what we'll do is we're going to set up a couple of flip-flops. This will be J sub A, K sub A with output A and A prime. This will be J sub B, K sub B with output B and B prime. And lest you think that this is trivial, we're just going to take outputs and connect them to inputs with a difference. And the difference is we're going to take B prime and wrap it around and hook it to J. I'm going to take B and wrap it around and hook it to K. All right. Can you see that all right? So looks all right, I guess. So now the question is, what does it do? This is actually a pared down version of what you're seeing in question 9, homework 10, which is a 4-bit Johnson counter. Let's do it with a 2-bit Johnson counter because I think we should start with 2 bits before we go to 4. So how do we do this analysis? Well, let's see. I need a present state and a next state, so let's start with all possible present states. Now, I can't just jump to the next state column because I don't know what it is without doing an analysis on the inputs. So let's write out JA. I'll write it here. JA, KA, JB, KB. And once we know that inputs, maybe we can figure out what the next states will be. So it says here that JA is equal to B prime. So here's B. Let's write out B prime. 1, 0, 1, 0. KA is always going to be the inverse of JA, 0, 1, 0, 1. And I can get JB, that's equal to A, 0, 0, 1, 1. And KB is always the inverse of JB, so it's always 1, 1, 0, 0. Now, let's take a look at how JK flip-flops work. If you got 0, 1, in the present state, we don't care what it is because the next state is going to be a 0 because that's asserted a reset. If you got 1, 0, well, we don't care what the present state is because the next state's going to be a 1 because that's a set. Right? In other words, if you set it, I don't care what it is on the present state, next state's a 1. If you're going to reset it, I don't care what the present state is, the next state's going to be 0, because reset. Reset makes it 0, set makes it 1, and that's it. That's how JK flip-flops work. So if I want the next state, A plus and B plus, all I have to do is figure out where the 1 zeros are, and there's the 1 0 here, and there's one here, and there's one here, and there's one here, and all the rest are 0, 1, which means everything else is 0. Does everybody kind of see how I got that? I hope I didn't go too fast. Is it clear? Right? This part in here. A little too fast. Okay, a little too fast. Let's take a look at the set JK and the reset for the JK. Set JK, J is a set, K is a reset. Now if you make J set and reset is 0, that thing's going to be set. Doesn't matter what its present state is, next state's going to be a 1. And if you make it a reset and the next and the present state and the set state is a 0, doesn't matter what the present state is, next state is going to be 0. Is that clear to people? That's how JK flip-flops work. So that should be good. And now I go in over here and I look at what the input is, right? And if the input's a set, then I know this little bit's going to be set. Here it's a set, so this little bit's going to be set. Over here it's going to be set, right? So there's a set. Over here there's going to be set. So over here there's a set. And all the others are reset. Is that clear? Can people see my video okay? Yeah? So go ahead. Two ones. Well, because this is saying it's going to do a set. Sorry, here's a set, right? So that's got to be set. And this one's going to be set, so that's got to be set. All right, so in other words, this A plus corresponds to the input for JAKA, and this B plus corresponds to the input for JBKB. They both have the same inputs, so you're going to have the same outputs. Is it clear? So for example, here it says reset, whereas here it says set, and that's why it went 0, 1. You see? Does it make sense? Well, if you want to, okay, think about J and K as set and reset, right? So if you want reset, you put in a 1 for R and a 0 for S, and that's going to do a reset. And if you want to do a set, you put a 1 for S and a 0 for R, and that's going to do a set. Right? So if 0, 1 is used on input, like over here and over here, then you expect the output to be 0. Here's a 0, 1, so output 0. Here's a 0, 1, output 0. Here's a 0, 1, output 0. Here's 0, 1, output 0. Right? Because 0, 1 says you're going to assert reset, and you're going to assert set as 0. Is it clear? Sure. So now let's number these things. 0, 1, 2, and 3. And let's number the next states. 2, 0, 3, and 1. So now I can write out present state, next state as a finite state machine diagram. I write 0 transitions to 2. 2 transitions to 3. 3 transitions to 1. 1 transitions to 0. And that's what we can expect from the twisted ring counter. That's our analysis. There's no gates involved, right? It's just wires and our knowledge of JK flip-flops. Let's have a look at what the pattern looks like, though, when we take this present state, next state diagram and we write it out in binary. So it goes like this: 0, 0, 1, 0, 1, 1, 0, 1, and then back to 0, 0. And that is called a one-hot counter because there's only one bit changing as you go from one transition to the next. this is kind of useful for doing things like running stepper motors. And that was part of the intro to homework number 9. I had this little thing about stepper motors. So now we've got this kind of interesting little counter, and we've done the analysis for 2 bits. Why don't we do the same exact thing with a difference? And the difference is, I'm quitting out of the app on my iPad to see if I can get it to go away from the list of participants. I may or may not have been successful with that. I got to check my participants list again. Just a minute, please. I've got like 27 people out there. Yep, I'm still in there twice. I don't know what's going on. All right. Here comes another version of what we just did. Just the same, with a little bit of a difference. And you guys ought to be able to work this out too. Let's assume we have the same exact setup with a difference. And the difference is, now we got 3 flip-flops. You can kind of see where this is going, right? So now we have the A, the B, and the C flip-flop, which means we're going to have A and A prime, B and B prime, C and C prime. I got to use graph paper for this because we're going to go to 4 flip-flops, and that means we're going to need 16 rows, and I just can't do that on an iPad. Here comes JA, KA, JB, KB, JC, KC. No questions about the setup so far, right? Everybody's okay. Now we're just going to hook it up. Outputs go to inputs. Just like before, we're going to take C and we're going to run it into K. We're going to take C prime, we're going to run it into JA. What does it do? Right, this is all part of the analysis, and it actually will help you to answer question number 10, but it's important that you learn how to do these sorts of things. So they call it a twisted ring because we have negative feedback on the outputs here. So let's do the analysis again. This time we have double the work because we added a bit. And lest you think I didn't try a tablet, I actually tried 2 tablets over the weekend, and I wasn't able to get satisfactory results from either because of the lag. So much latency in watching your screen while you're writing that I found it impossible. Although some people say it takes a week or 2 to get used to it. I don't want to get used to it. It's too hard. So anyway, here comes JA, KA. Right? And we know KA is the inverse of JA, and we know JA is equal to C prime. So take C and invert it. 1, 0, 1, 0, 1, 0, 1, 0. KA is the opposite of JA, so that's easy. And now we can do JB, KB, which is pretty cool because JB is just equal to A. So if we take A, draw a little line in through here, JB is equal to A, so 0, 0, 0, 0, 1, 1, 1, 1. KB is the opposite, 1, 1, 1, 1, 0, 0, 0, 0. So now I got another flip-flop done. Let's do another one. JC, KC. And now JC is equal to B, so that's 0, 0, 1, 1. You can see 0, 0, 1, 1. And KC, once again, is the opposite. How am I doing so far? Did I go too fast? What if J and K were both 1 or both 0? If they were both 1, it would be in a toggle state. If they were both 0, it would be in a hold state. You can kind of see that. Someone asks this question about JK and Q. So right in through here, this is the hold state. Right in through here, this is the reset state because K is asserted as 1. Right in through here, this is the set state. And then right in over here, this is the toggle state. So when you look at Q plus to see what the impact will be on the inputs versus the present state, if it's a hold state, it maintains the state. If it's a reset state, it goes and clears. If it's a set state, it goes and sets. If it's toggle state, you invert because it's toggled. And that's what happens when they're both 1 or if they're both 0. Is that good? But we're not seeing that here, not with this counter, right? So this counter basically says, look, 0, 1 is being used. So if I see 0, 1, which is here, here, and here, then the outputs A plus, B plus, and C plus must be all 0. Any place I see 0, 1, it must be 0. So I see 0, 1 is here, and I see it here, and I see it here, and here, and I see it here, and I see it here. Anywhere else I see 0, 1? Yeah, right over here. And that's it. All the rest are equal to 1, 0. Here's a 1, 0, so that goes there. 1, 0 goes here and here. 1, 0 is here. 1, 0 is here. Isn't this fun? Yes, Professor Lyon, very fun. And then 1, 0 goes over here. I see a 1, 0 goes there. Let's draw a little line over here. And there's a 1, 0. And here's a 1, 0. And that's a 1, 0. And now I have my present state, next state table from my remapped excitation table. What if J came to... Okay, so I guess maybe... What do you think of that? Did I go too fast? Any errors or blemishes? Let's number these things. 0, 1, 2, 3, 4, 5, 6, 7. That's 4, 0, 5, 1, 6, 2, 7, 2. Okay. So now I can extract my present state, next state table. How cool is that? 0 goes to 4. Right? We can see 4 goes to 6. 6 goes to 7. 6 goes to 7. 7 goes to 2. 2 goes to 5. Doesn't it? And then 5 goes to 2. Uh-oh. 7 goes to 2. 5 goes to 2. That doesn't look good. Sorry, so you're saying there's an error. I think you're right. Yeah, 0, 1, 1 should be 3. So from 7 we go to 3. Ah, very good. And then from 3 we go back to we go to 1. And then from 1 we go to 0. There was a little blemish. So looks like we captured all the states except for 2, right? 2. Where does 2 go? 2 goes to 5. Okay. Where does 5 go? 5 goes to 2. So 2 and 5 are left out. These are like the orphan cycle right in through here. And what we got for a regular cycle is 0, 4, 6, 7, 3, 1. And if you take a look at the binary, 0, 4, 6, 7, 3, 1, you get 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 0, 0, 1. So now you can kind of see the symmetry in what's going on. It's rolling ones into the digits, and then it rolls zeros in to replace them. And it repeats. So in this cycle, from 0, 4, 6, 7, 3, 1 back to 0, we've got a nice little finite state machine which behaves just the way we want it. But if for some reason you were to restart this entire system and it started at 2 or 5, it would just oscillate back and forth between these two things. It's not a self-starting counter. And if it gets in one of these two states, you'll be stuck there forever until you cycle power off. So that is the analysis on the 3-bit Johnson counter. What do you think of that? It says Q11 is 3. Yeah, that's correct. Thank you. What else? 011 is 3. Yep. So everybody on board with this? Is it time for the 4-bit? That's the one that you got to get for homework. I'm going to do the 4-bit one. And you can kind of see how this is growing, right? It's going to double in size if I go to 4 bits. Right? It's doubled in size when I went from 2 bits to 3 bits. From 3 bits to 4 bits, instead of 8 rows, we're going to have 16 rows. A lot more work. So you got to have the graph paper. Let's give it a go. Unless there's questions here. No? We're good. All right. Getting this iPad out of here. It's in my way. Okay. Fresh piece of paper. Okay. Now we're ready to do the same exact problem with a difference. And the difference is, I got 4 flip-flops, A, B, C, and D. A prime, B, B prime, C, C prime, D, D prime. And we've got all the same JKs. These are A's, those are B's, these are C's, and those are D's. Now, you got to hook them up. And it's twisted, so that means D goes to K, and D prime goes to J. And that's what we got. What does it do? Well, it's not obvious. Let's start off with all possible present states. Okay, now let's take a look at what the inputs will be given the wiring that we've got up in here. I know I've rolled it off the screen, but it's not really that hard to remember. We'll just start with the first digit. And what we know is JA is equal to D prime. So that's just this. And we know KA is the opposite, just like before. And now we've done 1 bit. Let's do it again. JB, KB, and it looks like JB is equal to A, so I'll just draw a little line over here. JB equals A, so I'll just put in all zeros. That's easy. You can kind of see why I need to use graph paper here, right? Keeps the lines going. And now KB is the opposite, so that's not too bad. Just invert JA. Now I did another bit. On to bit C. And C is equal to, well, JC is equal to C. And so we can sort of see how that worked out. It's going to be 0, 0, 1, 1. 0, 0, 1, 1. 0, 1, 1. 0, 0. 1, 1. 0, 0. 1, 1. This is fun, isn't it? Yes, Professor Line. Very fun. Oh, sorry. This is very serious work. So, now let's do the next bit. JD, K, JC is equal to B. Yes, it is. What did I write? Oh, crap. Oh, no. I have a blemish in my presentation. Oh, that's very bad. Oh. If I had my little iPad eraser, I could probably erase it. Let's do this again. JC, thank you. JC is equal to B. So it's 0, 0, 0, 0. Thank you for that. 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. I was having so much fun too. 1, 1, 1, 1, 0, 0, 0. Okay. Did we do it right this time? Excuse the blemish. There. Now let's do JD, KD. And now it says here, now I can write JD is equal to C, 0, 0, 1, 1. And KD is the opposite. There. Are we there yet? Thank God. All right, so now A plus, B plus, C plus, D plus. We want the next states. That was the whole point of doing this little exercise. So I got set, reset. That's 1, 0, 0, 0. I got reset, reset, so that's 0, 0, 0, 0. I got set, reset, that's 1, 0, 0, 1. I got 0, 0, 0, 1. 1, 0, 1, 0. 0, 0, 1, 0. 1, 0, 1, 1. 0, 0, 1, 1. 1, 1, 0, 0. 0, 1, 0, 0. 1, 1, 0, 1. 1, 0, 1, 0, 1. 1, 1, 1, 0. 0, 1, 1, 0. 1, 1, 1, 1. 0, 1, 1, 1. Did I go too fast? Everybody kind of following along a little bit? Just stop. Well, here it says, yeah, this is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. That's the present state. Now let's do the next state encoded in decimal. So that's 8, 0, 9, 1, 10, 2, that's going to be 11, 3, 12, 4, 13, 5, 15, what is this? 4 plus 2 is 6, that's 15, and that's going to be 7. Does that look about right to you? Yeah. That. Okay, so this is your next state. So A plus tells you what the next state of the flip-flop will be after the clock, which I didn't draw in, gives you an edge to trigger the flip-flop to listen to its input. So what will happen is, if you're in state 0, the stimulation of the flip-flops will cause it to change to state 8. And so that's what A plus B plus C plus D plus represents, the next state for the flip-flop, given the wiring diagram and the inputs to the flip-flop. What do you think of that? It's in, yeah, so A plus is the next state for A if the input for A is 1, 0. So in other words, because 1, 0 is being used on input, the next state for A will be a set state, because this says set and don't reset. Right? So if we remember correctly, if what you want to do is put in 1, 0 for J and K, the next state, Q plus, is going to be 1, because that says set. And if you put in an input 0, 1 for J and K, that's a reset, and the next state must be 0. Doesn't matter what the present state is. If you tell it to set, it's going to set. If you tell it to reset, it's going to clear. So here A plus says, in the next state, I saw a 1, 0 on input, therefore I must set. Is it clear? Sorry, is it set? Okay. So we did that for all the bits in here, and now we've got present state, next state, and now I can draw a finite state machine diagram. So let's start doing that. 0 transitions to 8. Okay? 8 transitions to 12. 12 transitions to 15. 15 transitions to 7. 7 transitions to 3. 3 transitions to 1. 1 transitions to 0. And a whole bunch of numbers have been left out. But one thing I can say is that 0, 0, 0, 0 goes to 1, 0, 0, 0 goes to 1, 1, 0, 0 goes to 1, 1. Did 12 go to 15? It sure does look that way, doesn't it? That doesn't seem quite right, does it? It should have gone to 12 should have gone to this. 1, 1, 1, 0. Oh, look at that. So this is supposed to be 14. I don't know why I wrote 15. Silly me. So it does go to 14. That's good. So this goes to 14. And then 14 goes to 15. That's okay. And then 15 goes to 7. Okay. Yeah, I was trying to figure that out. I was like, wow, why didn't that work? And it's because I don't know the binary. And if you don't know it by now, so let's do it again. 0, 0, 0, 1, 0, 0, 0, 1, 1, 0, 0. That's supposed to be 14. 1, 1, 1, 0. 1, 1, 1, 1. I will. Just a minute. 0, 0, 0, 1. And now it goes back to the beginning. So that is 0, 8, 12, 14, 15, 7, 3, and 1. Somehow my graph paper got a little damp. So here we go. And that's the way it's supposed to work, without the blemishes. How's that grab you? Good, right? But guess what? That's not the answer to question number 10. Why? Why isn't it? Well, because there's some missing numbers here, right? Let's take a look at what's missing. Let's see. It doesn't look like we hit 6. I went 0, 1. Wait, where's 2? I don't see 2. I got 3. I don't have 4. I have 5. I have 6. Where did all those numbers go? They're in another count, which is not part of the Johnson counter. So let's see. If we started off with, pick a number, 6, what's our next number? 11. So this is a whole other thing we can explore. 11 goes to 5. Okay. And 5 goes to, looks like it goes to 2. Right? And 2 goes to 9. Right? Yeah, 9. And 9, where's 9 go? 9 goes to 4. And then 4 goes to 10. And none of these numbers appear in here at all. And then 10 goes to 13. And 13 goes back to 6. Look at that. Here's a whole other counter, which does something completely different. Let's have a look. It's, I guess we can draw it out. 0, 1, 1, 0. All right, that would be 6. 11 would be 8 plus 4 plus 1. And then comes 5, 0, 1, 0, 1. And then 2, 0, 0, 1. I don't think this is all going to fit. 1, 0, 0, 1, 4, 0, 1, 0, 0. And 10. And then finally 13, which is, so what we got here, this sequence is the answer to question number 10. So the Johnson counter, as it's wired up here, was designed to make this sequence. But the unintended consequence of wiring it up in this way also enables you to get that sequence. So if you power up the device and you end up in any one of these states, you'll be locked in to a set of numbers that weren't the numbers you wanted. It's not a self-starting counter. And that is the answer to question number 10. Could be. Yes, it is. Where did we get? 6, 11, 5, 2, 9, 4, 10, 13. Does it match? 6, 11, 5, 2, 9, 4, 10, 13. Yes, it does. So now, let's take a look at the answer. And it says 6, 11, 5, 2, 9, 4, 10, and 13, which is what you want. So that's where you get the answer to question number 10. What do you think of that? Is it who's confused? Be honest. Anyone? I'm going to go over to the invite area and see if anyone's clicking yes. No, nobody's confused. Oh, that's good. So we were able to, interestingly enough, do 3 different reverse engineering problems, all of which did a deep dive examination on the, we'll call it the twisted ring counter, or the Johnson counter. They're both legitimate names for this counter. What do you think of that? Good, right? Want to try another one? Let's do question 11. That's a reverse engineering question as well. I like to tackle some of the harder questions, if that's all right with you guys, just so that you can have a chance to see what it's like to do the applications from chapter 7. You should... Did 11? Oh, yes, you did. Yes, I see that. 12. Sure, let's try that. I thought we already did 12.
We did 12, but the answer to the question was kind of unclear.
All right, so it says implement a 3-bit gray code counter using D flip-flops. Let's take a look at that. So I'm given a sequence. Let's get this little space here. And the sequence says, so that's my given. And you want to design a counter using D flip-flops. So we're given this sequence. Want to make a counter using D flip-flops. Let's start with the present state. This is question 12. I think my pen has run out. Ah! Just a minute. We're going to fix this right now. Okay. Sorry about that. You know what? I'm not too happy with the way that looks. I'm going to try something else. Let's see. What do we got here? Got a little marker. That may be okay. A little bit thick, but you can see it pretty good, so that's good. So from 0, we're going to go to 1. From 1, we're supposed to go to 3. From 3, we're supposed to go to 2. Wait a minute, what's going on here? From 2, we're supposed to go, what's going on? 0 goes to 1. 1 goes to 3. 3 goes to 2. 2 goes to 2? Yeah, that's what it says, huh? It's going 0, 1, 2. 2 goes to 6. 6 goes to 7. 7 goes to 5. 5 goes to 4. And I don't see what 4 is supposed to... Oh, 4 goes to 0. 0, 1, 1 is 3. Let me just write the present state, next state. 0, 1, 2, 3, 4, 5, 6, and 7. So 0 goes to 1. 1 goes to 3. 3 goes to 2. 2 goes to 6. 7 goes to 5. 5 goes to 4. 4 goes to 0. 6 goes to 7. So it should say 0, 1, 1, 3, 2, 6, 3, 2, 4, 0, 5, 4, 6, 7, 7, 5. So this should say, I guess I can write it if you like, 1, 3, 6, 2, 0, 4, 7, 5. I gotta say, this is too thick a marker for me. So I think I got it right. What do you think? This is too thin. I'll find something better. I'm sorry, my pen failed me in the middle of this thing. I got another one. Jeez, I'm really striking out. I'm going to go to pencil. So now I'm supposed to do this with D flip-flops. So D sub A, D sub B, and D sub C. And now, one thing I know about D flip-flops is if you want this to be the output, that's what the input should look like. Is it dark enough? I may have to change pens again. Boy, do I hate changing pens every 2 seconds. Sorry. Here, red. Red's nice. I like red. Who doesn't like red? So now, I guess it's time to start to think about how we're going to create a minimum sum of products form for this particular system, right? And we're supposed to do it with D flip-flops, it says. So one thing I can do is I can put out a K-map. Boy, this is not looking nice. B, C, and A. That does not look nice. I'm going to go back to my little pencil here. And it's supposed to number the truth table 0, 1, 2, 3, 4, 5, 6, and 7. Go back to the marker. Okay. So now, yeah, sure. And now I got ones. Oh, yes. That's better. Thank you. So now for, make sure this gets on the screen. Rows 2, 5, 6, and 7. I got loops in through here, and that'll give me BC prime and AC. And that'll be the input to D sub A. And now I'm going to do it again. This time with a slightly larger. We'll go to 1, 2, 5, and 6. And I got a loop here and a loop there. And this loop is going to be BC prime. And this loop is going to be B prime C. And so now I can write D sub B is equal to B exclusive or C. And we got one more K-map to do. Although, I wonder if there was some trivial thing we could write here for D sub C. I guess not. Well, wait a minute. Is it B prime? No, maybe not. Okay, so 0, 1, 6, and 7. And these two are obvious loops, A prime, B prime, and AB. So D sub C is equal to AB or A prime, B prime. So that's my design. So now what do we have for our solution? Looks like our solution is showing us 2-bit. Is this where we went wrong last time? If we do it with a 2-bit and toggles, did we change this? We did it with toggles last time. So I think I went through and I changed this online. Did you happen to notice the changes online? We went through and we did it with toggles. If you do this with toggles instead of, see, there's two questions here. Now I remember what happened. It says here, 2-bit gray code counter is given by 00011110. Implement this with toggle flip-flops. Then it says, implement a 3-bit gray code counter using D flip-flops, which is what I just did. However, that was a spurious question. It should have just been implement the 2-bit sequence, which says, oh gosh, 00011110. That's a much simpler sequence, right? Implement that sequence using toggle flip-flops. Totally different question. Right? You can kind of see why that's a totally different question. First of all, it's 1 bit less. Second of all, it's using different flip-flops. So if you go through and do that, then what you get, and I'm not unhappy with the idea that we showed how to do this with 3 bits and D flip-flops, because that's a reasonable thing to want to do. Take the present state next state equation, which is going to go 00011110, and then repeat, and code it in decimal, 013. Oh, sorry. And 2, return to the beginning. And now we can write the following. Present state, next state, 0, 1, 2, 3. So from 0 we go to 1. From 1 we go to 3. From 2 we go to 0. And from 3 we go to 2. And now we can encode this in binary. And we encode it in binary by writing present state A and B, 0, 0, 0, 1, 1, 0, 1, 1. Number the states, 2, 3. And then get the next state as A plus B plus. And then 0 goes to 1, 1 goes to 3, 3 goes to 2, 2 goes to 0. And now, if you want to implement it with toggle flip-flops, if there's a change in state from 0 to 0, there's no change, but here there is a change, we write 0, 1. Here we see a change, there's no change, 1, 0. Here there's a change, there's no change. Here there's no change. Here there is a change. So now it looks like T sub A is equal to T sub B prime, or T sub B equals T sub A prime. T sub A is equal to A exclusive OR B. And T sub B is equal to A exclusive NOR B. So that's equal to AB or AB, which is AB prime or A prime B, and that's equal to AB or AB with 2 primes at the end. So that's the implementation. Now let's take a look at the answer. And what we have for an answer, We got an exclusive OR for T sub A, exclusive NOR for T sub B. And sure enough, here's the answer. Exclusive OR for T sub A, exclusive, that should be exclusive NOR for T sub B. Do you have a bug in the answer key? Oh, here it is. Right down in here. So this is what the answer should be. So it looks like indeed there is a little bit of a bug in the answer key. I assume you guys caught that, and that's why you were asking for clarification. I'm going to have to go in and fix that, but some people may have already taken the test. So without changing the answer key, I shall replace this over here, and this will come down over here so that the correct answer is shown. So we'll swap that, so anyone who's already taken this and gotten a correct answer won't get penalized. That's all right. So it's clear. So there's a bug in this question. More than one, actually, because when we look at the original question, right, what do we see? The original question, for some reason, had implement a 3-bit gray code, and right under above it, it says implement a 2-bit gray code. Well, you can't do both. You do one or the other. So this has to be removed. All right, that's a bug, and the answer key has to be fixed. Sorry about that. But in any case, we got that squared away and we found the error, so I'm glad for that. Thank you. What other questions do you have? You wanted me to do number 13, was it? 13. Let's look at that. I'm just going to grab the question. This is a true-false question. And what he says is, the following 2114 holds 1K bytes of RAM. That's 1K by what? Is it 1K by 8 bytes of RAM? 8 bytes would mean, well, I guess 8 data bits. Can you get 8 data bits from this? And the answer is no, you cannot. Why? Because it's only 1K by 4 bits of RAM. So this is not holding a kilobyte. It's holding 1024, we'll call it nibbles, right? 4-bit bytes, 4-bit words. So in order to get 1024 addresses, I got to have A0 through A9. I got to have 10 bits, because 2 to the 10 is equal to 1024. I said 4, but I wrote 5. 1024. Here, I'll write it again. 1024 equals 2 to the 10. There. And then that means you need addresses 0 through 9. That's 10 bits. But when you look at the data bits coming out, there's only 4 of them. That says D0 through D3. So in order to get 8 bits for bytes, right, because it says bytes, and 1 byte is 8 bits, you've got to have 2 of these things. And so the correct answer is false. It does not hold 1K byte, right? It holds 1K nibbles. A nibble, I'll just say nibble, N-Y-B-B-L-E, equals 4 bits. And you can see the answer on that. And if you look at the book on page 358, it actually shows this. So if you're reading along and you go to page 300 and let me see if I can show that one to you. This is like right out of the book. 358. There it is. Right? So it's only got 4 bits coming out, and it says right here it's 1024 by 4 bits of static RAM. So sometimes it helps to read the book. I know some people don't want to read the book, but look, it's right there in the book. So that should help you. When you start to learn about computer parts, it's kind of important to know about things like RAM, because that's sort of a part of the computer. Right? It says, the diagram on 13 is also very small. Can we do 15, 17, and 18? Yeah, it is a little bit small. In fact, my camera isn't picking it up nicely, but if you're looking at it online, I think it's clear. Can we do 15, 17, and 18? Yes, we sure can. Let's do that. 15. So last time we saw the Johnson counter, in our last exciting 4-bit example, we saw this very interesting looking sequence. And this very interesting looking sequence actually happens to be the answer to 15. So if you're looking at that sequence and then you compare it with the selected answers, you will find it there. And so that's a good time, right? So that'll give you the answer to 15. So in addition to being the answer to 10, this is also the answer to question number 15. So that's 15. Then somebody says, can we do 17? Yeah, sure, you betcha. How am I doing on time? I got 5 minutes? I can do 17. What does 17 say? A barrel shifter. Barrel shifter. Let's just show the question here. So here's the barrel shifter. A barrel shifter is a digital circuit that can shift a data word by a specified number of bits without using any sequential logic, only purely combinational logic. A 4-bit barrel shifter with inputs A, B, C, and D. The shifter can cycle the order of bits as B, A, B, C, any order you like, and it can do it in 3 gate delays, and it does it with these multiplexers. And so the multiplexers essentially can choose which input goes to where. And you can do that with this little address thing. So this little addressing thing says which bit will come out of here. And you can choose one of the 4 bits. And so by using this technique, and because the bits are rearranged depending upon which multiplexer you're on, you can choose to pick any one of the inputs, and they're all wired to different places. So this one's wired to bit 1, that one wires to bit 2, this one wires to bit 3, this one wires to bit 4. But then if you shift down by 1, this one wires to bit 4, this one wires to bit 1, this one wires to bit 2, and this one wires to bit 3. So you basically shifted everything over because of how it's wired. Similarly, we can see this is shifting from one bit to the next bit. Here we can go here, it's going to the next bit, here it goes to the next bit up, here it goes to the next bit up, and here it goes down. And similarly, they're all wired differently, and so when you go through the permutations 0, 1, 2, and 3, you'll get different outputs as a result. And so you can effectively look at this by inspection and say, yes, this is all going to work in 3 gate delays. All you have to do is choose how you want to have the bits arranged, and then you can get that arrangement directly out from your 4-to-1 multiplexers. And so you've got an opportunity now to do sort of an application of multiplexers to make a shifter and do it all in 3 gate delays, which is kind of cool, actually. Someone says, can we do 18? Okay. So 18 looks like this. So this is a bipolar junction transistor, and that's a bipolar junction transistor. And these 2 bipolar junction transistors are cascaded together. The current on this transistor is then used to switch the current on that transistor. And by cascading the two transistors together, you can obtain a higher current than by using a single bipolar junction transistor. And together, it's called a Darlington transistor. And that gives you a higher current by using two bipolar junction transistors. And you can actually get these in an array in a single chip, and it will drive stepper motors from something relatively low current like an Arduino. So the answer to that, and there's your collector and there's your emitter, these two transistors can be made to look as though they're one transistor. Even though the switching speed suffers a little bit, you get a lot more current. And so here is the chip, and it's called the ULN 2003, and it's got 7 Darlington transistors in a package, and this will give you the ability to drive high current outputs. So if you're doing a senior project and you're trying to get high current stepper motors to run, you can do that with chips like that, and we have these chips in the stock room. So that's cool. And the answer is true. And somebody asks, can we do number 14? I got 2 seconds. I don't know. Maybe not. Oh shit, no way. I'm so sorry. This is something. Yeah, number 14 kind of looks like this, and that requires a substantial amount of analysis, which you're going to have to do on your own because we are out of time. So, sorry about that. But what you're going to do, and here's the approach, right? You're going to write down the equation for each one of the inputs, including this one down here at the bottom, and then you're going to write out what the next state will be after you've written out the present state. And this is A, B, C, and D, so you'll write this out. And in fact, this is 0, so you can eliminate it and just do B, C, D. And when you look at the inputs, you should be able to figure out what the equations are by inspection. And once you've got that, you should be able to write out what the toggle flip-flop inputs are, and that'll give you the next state. And it's important that you be able to do this kind of a problem, because this is the kind of problem you'd see on the final. This is actually, yeah. Well, I can do it if you like, but how many people here have to go? Just just give us a yes. Should I do it? I'll do it. I don't care. I'm not going anywhere. So yeah, let's get a fresh piece of paper. Actually, I wonder if I can just write it out here. It's not very clear in the camera. I'm going to have to do this with a fresh sheet of paper. Just a minute. There. So that says C prime D prime. Actually, I can write some of it out here. And that says B prime C prime. And I think that says B C D. Yeah, this is going to get too crammed. I'm going to have to redraw it. It's going to take some time. Why don't you guys tell me what the inputs are here while I'm drawing this? Any takers? I don't think it's healthy for me to just do all of these for you. Can you not tell me what the inputs are here? Uh-huh. Mm-hmm. Okay. And what do you got here? Mm-hmm. Okay. What about over here? That's what I see. Yep. Mm-hmm. All right. So then it turns out we can write out equations for T sub D as C D prime or B prime C or B C D. T sub C must be equal to BC prime, B prime D, CD prime. T sub D must be equal to BD prime. And when that should have been a B, right? T sub B. That's BD prime, B prime C. And that's what I got, right? And T sub A is equal to 0. So let's ignore T sub A and just write out B, C, and D. And now what we can do is write CD prime means we need a 1 and a 0 here. B prime C means we need a 1 and a 0 for, a 0 and a 1 for B and C. Got that already. BCD means we need 1, 1, 1 for the least significant 3 bits. It's here. All the rest are 0. Now we can do T sub C, which says B has to be a 1, C has to be a 0, so 1, 0, and the most significant 2 bits. That's these 2 rows. Then it says BC prime. Now B prime C is going to be 0 in the most significant bit and 1 in the least significant bit. 0, 1 is here, and all the rest are 0. Now let's do T sub B. Oh, did we get that wrong? I got 1, 0. So that's going to be a 1 and a 0. That's right. And that's right. Then I got 0 and a 1. 0, 1. That should be a 1. That should be a 1. And then I got 1, 0. So that should be a 1. that should be a 1. Okay, now I think I got it right. Now we'll do, oh, I'm going backwards, am I not? Shoot. The labeling is backwards up here. I have to relabel everything. Darn it. I should have started with this one on the bottom and written it here, and then gone to this one for the middle. That's correct. And then this should be over in here. So that what we can do is write T sub D, T sub C, T sub B, and then if you want you can reverse the columns later. What a pity. T sub B is going to be 1, 0. So that's going to be 1, 0. That's here and here. And this is going to be 0, 1, B prime C. 0, 1 is here and here. The rest are 0. So rewrite this so that the columns are in the correct order, and then you'll be able to figure out what the next states are. And then you'll have a present state, next state diagram. And that's how you do that. And I can finish this up in the next section. I think I need a 5-minute break, and probably you do too. So we went over a little bit. Sorry about that. Sure. So I will finish this up in the next section, which starts in about 4 minutes. I'm going to take a bit of a break myself. I need some coffee to keep going. Enjoy the rest of the day and stay safe. Thanks a bunch. Thank you.